Hello and welcome everyone to the channel. This is CCNA course day 24 and I'm just going to speak about concepts of EIGRP in this video. EIGRP is a part of CCNA course, so you can easily skip this lesson and go to the next one. But I suggest that you take a look at this video because this is going to teach you something new, and that would be really nice if you know this, because in real world networks, EIGRP is one of the very widely used protocol. Maybe in system service providers this is not going to be used, but in data centers EIGRP is a very valid solution. So let's see where we use this knowledge. So even if this is not part of the blueprint, you need to know because real world Cisco networks still use it. And also when you understand this, you're going to understand a lot of fundamentals really fast, specifically because this is a little bit different from IS to IS and OSPF. They are something that we call them shortest path first protocol, or what we call them linked state protocol. Here we have something that we call it distance vector protocol. And it is not like linked state protocols. In linked state protocols, like I said, everyone inside the area shares the same database, shares the same house, shares the same image. But in EIGRP, like RIP, that I have spoken about this before, we only know what our neighbors tell us. But so again, we can just take a look at this and understand what it is, this protocol and how this works. So we have EIGRP as an advanced distance vector protocol. Compared to RIP, of course, this has some extra great features that you can already find it in RIP. For example, we don't really have any let's say limit for the number of hubs from the source to the destination. In RIP that was 16. We have something that we call it region. A region is called an autonomous system in EIGRP, so you can have multiple regions in your network. And also, instead of adding the networks classfully like we did in RIP, here we can be classless, which means that subnet masking is supported here, variable length subnet masking, and CIDR is supported here. Also, we have very fast convergence in EIGRP, which is great. And also, configuration of EIGRP is super fast and easy. So the next thing that you need to know is what is the behavior of a distance vector protocol. So a distance vector protocol learns the routes from its neighbors. I have spoken about this before when I was talking about RIP. I told you that when I have neighborship between me and another router, then what is going to happen is I can learn from that router what prefixes he knows, or it knows, actually, because I can already specifying a gender for routers in here. So let's say, for example, in my case, I have router 1 here, and just go with another one. Okay, this is router 1 here, router 2 is going to be here, let's say router 3, 4 is here, and 5 is here, and let's say there is a router 6 in here. We can have multiple paths from the source to the destination, and configuration is going to be different. I can tell, for example, that there is a ring topology in this case, and I have this section here, which is a section of 10.0.0.0 slash, let's say 24, for example. And on this side, I have another network, which is 192.168, let's say 0.0/24. Okay, I want to know how I can receive information from router 6 to router 1, and assuming that every router is connected to the other one and is adjacent with the other one using EIGRP, things happen like this. Router 6 knows all the connected networks about this, and it has it inside its topology table. Then router 6 and router 4 through hello messages know each other, and they can create an adjacency. This means that router 6 is going to send all the updates to router 4, and so does, of course, router 4. And then router 4 is going to understand that router 2 is another EIGRP speaker in the same region or in the same autonomous system, I would say. And then they can be neighbors, and router 4 is going to send information to router 2. Router 2 is neighbor with router 1. Again, the same thing. Router 2 is going to send information to router 1. If I have EIGRP speakers on the bottom leg, router 6 will send information to router 5, then router 3, and router 3 is going to send it to router 1. So router 1 is going to receive information for 10 000/24 prefix from two different places. One of them is going to be router 2, so it says that from this network, which is, let's say, for example, 10.1.2 is one of the advertisers, and the other one is 10.1.3.3, which is this one. So I have received this through two different places. But do I really need to install it inside my topology table and from there into my routing table? That's going to be another topic. What we do here is we calculate a bandwidth. For calculation of calculation metrics. For calculation of the metric, we need multiple values. And what are these values? We call them K values. A K value is a value which is going to go inside the calculation formula, and then we are going to receive a metric in the end. So what are the K values and how can we use them? There are 5 K values. There is going to be a 6th one in the newer version of EIGRP, but the 5 ones are going to be very important. The first one is going to be bandwidth, and you can use the bandwidth value and you can multiply it with any number. This number can be from 0 up to 255, which means that if you go 0, this means that bandwidth is not going to be calculated at all, because any bandwidth multiplied by 0 is going to give you 0. And 255 is the highest value possible. This means that you are given the utmost priority to bandwidth. The next one is, let's say, load. And load is going to have the same thing. So we can just say, okay, I don't care about this. This means that I'm going to multiply it by 0, or I can say this is very important for me. I can multiply it by any number from 1 to 255. The next one is going to be delay. So delay again is the same thing, 0 to 255. Fourth one is going to be, let me just find a better place for that. Fourth one is going to be reliability. Reliability, where's my pen? Reliability. Same thing, 0 to 55. And finally, we have MTU. MTU can have another value of 0 to 255. Okay, how can I use these and which one of them are used? It depends on the platform that you're using, and most likely you're going to see 2 of these values which are going to be important. One of them, let me just go with red again, is going to be bandwidth. So we are going to use bandwidth, but how important is bandwidth? We are going to use a value of 1 multiplied by bandwidth. So from 0 to 255, I have decided to multiply it by 1. Load is not going to be used because today's networks are super fast, and you are not going to put any load on the interface or on the link. Delay is very important. So networks is very much delay sensitive, so you need to incorporate this into your formula. So I'm just going to multiply it by 1. Reliability, my network is super reliable. I can tell all the ports are going to be up, and there are very rare moments that we lose a port or a link. So I'm just going to say reliability is not going to be part of the equation. And finally, MTU is a fixed value. Most likely you are going to see this as 1500 on a normal network and 9216 in a data center. So I'm not going to use this as well. So we have these values as K1, K2, K3, K4, and K5, and you can see that only K1 and K3 are used, which means that bandwidth and delay are used for the calculation. So with this information, you can see that I am using more criteria than what I had in RIP for calculation of metric. Even OSPF only uses bandwidth, and it doesn't really have calculation like this. So you can see that EIGRP is very, very smart in calculating the metric from the source to the destination. And the values that you see for EIGRP, they are very big values, and rarely do you see a difference between, do you see a similarity between metric from 2 different paths? So assuming that from router 1 to router 6, I'm using the same speed links, the same bandwidth links, what is going to happen is some of the links might have a little bit more delay than the other ones. Well, some of them a little bit less delay from the source to the destination. So what you're going to see here is the calculation is going to give you two different values, and the best value is going to be installed in your routing table. And in rare cases, when you have two values which are very similar, they are going to go into routing table, and you're going to have something that we call it equal cost multi-packet. Okay, so how do we use this bandwidth? Bandwidth from the source to the destination is calculated based on the lowest bandwidth that we have for our links. So if I have something like, let's say, 100 megabit per second here and 1 gigabit per second here, 1 gigabit per second here, the lowest amount is going to be this 100 megabits. So this is going to be used as the calculation for the bandwidth. And what about delay? Delay is cumulative. So if I have something like 2 milliseconds here, 3 milliseconds here, and 3 milliseconds here, then I'm just going to add all them up, and I'm just going to have something like 8 milliseconds of delay. So the lowest bandwidth through the link and a cumulative amount of delay is going to be used inside my formula. So that is how you're going to calculate the metric for your network. Let's go to the next slide. So what we have here is a picture list. If there is no change in the network, I'm not going to send you any update. This means that my network is going to be silent and stable. So I am going to send you an update when there is a change in network. Neighbor discoveries are going to be done with hello messages. You have seen this in in OSPF, and the same thing happens in almost every routing protocol that we have in here. Reliable delivery for updates. Fast convergence using dual. This is very fast. We can see that adjacency is going to happen super fast, and also in case we don't have any active prefix, everything is going to converge from the time that we lose a path towards the destination up to the time that we find a newer one and install in our routing table. That's going to be super fast. And also for EIGRP, we can have IPv4 support and IPv6 support. For RIP, of course, there is the same thing. There is another protocol which is called RIP Next Generation. For OSPF, we have OSPv3. Here we have EIGRP v6, which is going to support IPv6 for us. Okay, there are three different tables in EIGRP. This is important to understand. We have a neighbor table, which means that we are going to install information about our neighbors in that table. We have a topology table, which means that everything that I know is going to go inside that. Now, the topology table name is a little bit, let's say, misunderstood. This is not about the topology of the network. This is only the prefix that I have. And before installing this inside my routing table, I'm just going to put it in the topology table, and I'm just going to compare some values inside that so that I can make sure that this value is the best one, and I'm just going to put that in routing table after that. And of course, from routing table, it goes into, let's say, self table, in case we call it forwarding table actually. So these three tables are going to be important for you. But like I said, topology table is not similar to what you call it topology in OSPF. In OSPF, topology is an image of the network. In here, topology is just the prefixes that we have inside the router. Neighbor discovery is going to happen when two routers speak EIGRP. So understanding this is going to help you in troubleshooting. And if there is an adjacency problem, you are not going to, overthink it. You can easily find the problem. The first thing is, through hello messages, routers are going to exchange some information. And through that, this information is going to make sure that these two routers are going to be neighbors or not. For example, if they are in the same autonomous system, or if they have the same kind of authentication, this is going to happen for you. So autonomous system numbers are going to be important. Another criteria which is important is the same key values, because we want to calculate metrics, right? So if I do not have the same key values, I cannot really create metrics and then send it to my neighbors because we have some differences in here. Hello timers and hold timers are important. Again, what is hello interval? How often I say I am alive. What it means is I send hello packets to you every few seconds, and based on that, you can understand that I'm here. If I cannot send you any hello message, you're going to wait for some time, which is called the hold timer. And after that, you're going to pronounce me dead. You're going to say, okay, I cannot hear from my neighbor. So this means that my neighbor is dead. I am not in touch with it anymore. And when it happens, of course, I need to reconverge. What it means is I'm going to figure out how to reach the prefixes that previously I reached through you. So this is important, and you need to account for it. And also something that I just forgot to tell you is hello timer is very important, but hold timer is not, because you don't really have to match the hold timer. And you can say that hold timer is for the neighbor, hello timer is actually for you. There is something that we call it RTP, Reliable Transport Protocol. This is the protocol used to send updates to your neighbor. And because of the nature of this protocol, what we need to do is to make sure that we acknowledge the receipt of anything that we have. So EIGRP uses multicast and unicast. Multicast is going to be used for hello messages. Unicast is going to be used for sending information and updates to the other side. And also when we send the updates, we are going to have a sequence number on top of that, which means that the neighbor is going to know if it has missed any of my updates. So if there is a missing acknowledgement, which means that the neighbor has told me that I have not received this, then I'm just going to send that specific packet or specific part of information again, and it is going to receive it and install it in its network. And the packet types that we have in here, there are different types of packets in EIGRP you need to know. The most important one, of course, is going to be hello messages and update messages. But we can have some other types of messages. One of them is a query message. So let's say that I have lost one of my neighbors, and the prefixes that I usually to reach them through this neighbor now are not available. So what I'm going to do is to send some queries to other neighbors. And I'm going to say, okay, for this prefix, I used to go through router 1, for example, but now router 1 is not here. Do you have any path available to reach this specific prefix? You're going to send me a reply, and in that reply, you're going to say, yes, I know that, and this is the new path, and then I'm going to receive this, and it's going to be installed in my routing table. If you don't know, then you're going to forward this query to your neighbors. And if your neighbors don't know, you are going to forward that query to the other neighbors. This process is going to keep me waiting for this specific prefix that I'm trying to find a path for. And for this, we call this stuck inactive. This means that I am stuck in active mode for this specific prefix, and I'm just going to wait unlimited amount of time until I receive a response from someone. And there are, of course, some ways to stop this from happening, but right now this is not going to be our concern. But what we need to know is these are the packets that we have, and also the edge packet, which means that I have received the packets from you, so you should know that you don't really have to send it again to me. The brain for EIGRP, or the formula, is the dual. So dual, you don't really need to know about that, but you should know that this is the algorithm that is going to calculate the metrics for us. And based on that, of course, it's going to make sure that EIGRP doesn't pick a path that loops back to us. So loop prevention is going to be another let's say a feature of dual. So it chooses the base path and loop pre-backup. It keeps EIGRP stable during the failure. Also, it avoids routing loops during convergence. The key terms are very important, and these are some of them are going to be a little bit maybe hard to understand. So for that, I'm just going to draw something. I'm going to draw this router 1 in here. Let's say router 2 is here and router 3 is here. And here is the prefix that we want to know. That is going to be 10.0.0/24. And router 3 sends it to router 2. Router 3 says this is a connected network and my cost to reach this network is something like 10. So it's going to send this to router 2. Router 2 is going to receive it. And it says, okay, I have a cost of 100 to reach router 3. So I'm going to say I have a cost of 100 to reach the router tree. I'm going to add it to the 10 that router tree said is the cost to reach to the prefix. So to reach to the prefix, I will have a cost of 110. So you see that this 10 has been reported to me from router 3. Router 3 told me that it has a cost to reach to that prefix, and that was 10. That is called reported distance. Okay? What is 100 that is here? My cost to reach to router 3 is 100. So that's going to be my cost from here to the neighbor. What is this 110? This 110 is going to be my total cost. I'll call it a feasible distance. So two values are important. Reported distance is the value that my neighbor tells me. And I'm going to add it to my cost to the neighbor. That's going to give me the feasible distance. Okay, router 1 is going to receive this. Router 1 says, okay, my neighbor said that its cost is 110. That is the reported distance. My cost to router 2 is 100, so I'm just going to add it. So I'm going to have something like 210. My feasible distance is going to be 210. My reported distance is 110. So these two values are very important. So feasible distance and the reported distance. If feasible distance is less than reported distance, this means that there's a loop. Okay, how can this happen? Say router 3 is directly connected to router 1. Router 3 says the same thing to router 1. It says that my cost to reach to here is 10. Router 1 says, okay, from me to here, I have a cost of 150. So it told me that the cost is 10. I have 150 to get to here. So overall, I'm just going to have 160. So feasible distance from this path, this is the reported distance from this path. Feasible distance from this path is going to be 160. I have a feasible distance of 210 up here, which means that I have something which is, reported distance of 110, which means that I have something here which is less than this feasible distance. So I can keep it in my routing table, in my topology table, of course, and not in routing table, because I'm just going to install this one in my routing table, right? So the reported distance is less than my feasible distance towards the destination. Also, I can say that my feasible distance is less than the reported distance. Is more than the reported distance, actually. So here 160 is more than 110. That's okay. So now let's just say something is going to be different. In this case, let's say that, for example, the reported distance is 10 actually, which is okay on this link. And say this is super fast link, and I have calculated something like 90 from router 1 to router 3, which is going to give me an overall cost of 100. This means that router 1 sees a feasible distance of 100 here, a reported distance of 110 there. This means that router 1 is going to say, okay, this feasible distance is more than this reported distance, which means that this is going to loop back to me. Why? Because I'm just going to report it to here, and router 2 is going to prefer this path. It's going to use me towards the destination. So the feasibility is when we have this kind of a configuration. So it says a feasible successor is going to be the loop pre-backup in topology. So in my case, I had two paths. If I had the first calculation, then direct path would be the actual path, and the second path, which was a little high in the metric, that would be my feasible successor, and I would keep it in my topology table, and I would use it in case I see that my first path goes down. So the feasibility condition is something like that. Reported distance should be less than feasible distance, or I would say feasible distance is more than reported distance. Why interface bandwidth setting matters? So you can just change the bandwidth setting inside an interface. This means that EIGRP is going to use that value for the calculation. So if you set something wrong, then you're going to see something calculated wrong actually. So be very careful about the configuration of the interface and make sure that you are using either the actual bandwidth of the interface, or in case you have some SLA agreement, then you're going to use something less than the actual bandwidth, and that would be the actual bandwidth which is allocated to you. And something which is called equal versus unequal cost load balancing. Again, this is going to be something important. So say, for example, I have this towards destination, and let's say there's another one in here, and router 1, 2, 3, 4 are present in my network, and I'm trying to reach to 10.0.0/24 in this segment. So what is going to happen? In case, for example, I have the same bandwidth on here and on here, then what I'm going to do is put both of them in my routing table. I would say I can reach to 10.0.0.0 through, let's say, interface E00 and E01, right? That's going to be what I have in my routing table, because both of them have a metric of, let's say, 100. That is being these two are going to be used. And what I call it is equal cost multi-pathing. So I'm going to send some packets through Ethernet 00, some packets through Ethernet 01 towards the destination. Almost every routing protocol has such feature, but in EIGRP we have another feature. So let's say that I have different bandwidths from here to here, or like I said, delay is going to be different. So what I have here is, on this path I have a metric of 100, on this path I have a metric of 105. So which one is going to be installed in my routing table? This 100 is going to be installed in my routing table. But there is something that we call it a variance variable. If I apply variance, I'm just going to say whatever I have here as the least value, which is 100, if I calculate, if I want to use others, I can say, okay, 2 times this value is going to be okay. So 100 by 2 is going to give me 200. Anything that is less than 200 is going to be used in here. So 105 is going to be eligible for me. So this is what we call it as unequal cost load balancing, or UCMP, actually, multi-pathing, not load balancing, UCMP, and that is only supported in EIGRP, which is a very, very great feature. So overall, I just spoke about everything very fast, and I just gave you some little detail about the protocol, but that's going to be enough for you. You understood what neighbors are, and what are the three tables, what is dual algorithm, and what are the criteria for you to calculate the metric, and what are the backups, what are feasible distance, reported distance, and feasibility condition. And also, in the next video, I'm just going to talk about configuration and verification, and I'm going to clarify some of the concepts that I spoke about. As usual, like and subscribe to the channel. Also share this video with your friends, and hit that bell button so that you're going to be notified anytime I upload a new video. See you later videos.